Hello. Today, this presentation, I'm going to describe the hierarchical instance of my Sparsey model. So in the first place, Sparsey is a model of an individual cortical coding field that represents information in the form of a particular kind of sparse distributed codes. Each of the blue hexagons here corresponds to one Sparsey coding field, and we don't see the internals here. And well, let me show you what that would look like. So, right, so this is one tiny instance of a coding field that I propose as an analog to a macrocolumn, or really to a particular coding field in a macrocolumn. For instance, the level 2-3 portion of a macrocolumn. So there is the construct of a mini column, an anatomical construct in the brain. It may have a function as well, but mostly it's been defined anatomically. Which contains about 100, 110 neurons of various sorts. Layer 2-3 might contain 20 pyramidal cells plus some other stuff. So this, what I'm proposing here is that a mini column, or the L2-3 portion of a mini column, that set of 20 pyramidals, functions as a winner-take-all competitive module, so that in any one instance, for any one code or stored memory, only one of those 20 pyramidals would be active. But there would also be one active in all of the other mini columns in that macro column. And as a group of that set of active cells, which is a sparse subset of the entire L2-3 coding field, that corresponds to a memory or an engram or a code of an input. So in this little example here, there are 7 of these winner-take-all modules. Q equals 7, so I use Q to represent the number of modules. And each one has 7 pyramidal cells, which I represent as binary units. So Q is 7, K is 7 here. But in the brain, Q is 70 or 100. There's like 70 or 100. In hypercolumns, there might be 150 mini columns that comprise a hypercolumn. So Q would be 100, 150 there. And again, the number of pyramidals in the L2-3 portion of a mini column, this might be constant through most of neocortex, let's say 20. So K would be 20. So it's a huge code space. But note in particular that all codes are of exactly the same size because they all consist of one active pyramidal in each of the Q CM. So all codes stored in a sparsely coding field are of the same size Q. This is a picture of one particular code that was just picked at random, let's say, and I use phi to represent the codes, the names of the codes, or that they are codes, that may have been, that is assigned in this example to an input in a little patch of visual space, or really of LGN, part of the visual part of the thalamus, representing some little edge that's present in that portion of visual space. And the weights have been increased from these LGN projection cells, or we can think of them as just pixels, binary pixels, to the all Q of the units comprising that code. So that is the formation of an association from an input to a code, or the storage of a code or a memory representing that input. So that's just background. I go into the details of how the nature of these codes and how they're learned and how they're retrieved elsewhere. Today, I want to focus on the hierarchical aspect. So getting back to this picture, the application I have open here is a GUI front end to my Sparsey application, where you can create networks of arbitrary size, arbitrary numbers of levels. This one has 4 levels. One input level that's 42 by 60 pixels, binary pixels, that's down here. And then a 2D array, or a sheet of macro columns at the first internal level, L1, which is, I would say, in this visual example, this is analogous to V1, or some central portion of V1. And then above that, another sheet of macro columns, perhaps analogous, proposed as analogs of V2, and then the third one be an analog of V4. So there'll be flow of information from the input surface, which we can think of as the LGN representation, upward through V1, codes become active here. They send feed-forward signals, via U projections in the white matter underneath the cortex that arrive at V2, where a set of codes will be chosen to represent the V1 representation. And then signals propagate up to V4, and whatever codes become active here, the union of those codes would be representing the union of the codes active at V2 and recursively down to the bottom. So we're going to be thinking of hierarchical traces consisting of many of these sparse distributed codes active at the same moment, representing an input. Now, the inputs in this case are going to be sequences. They're from videos. So the model I'm showing here will, during its training trial, was presented with one sequence of 14 frames. It's from the Wiesmann data set. We pre-processed the inputs to look like this. So this is a 14-frame sequence. I'll just run it here, of a person bending down. Okay, this is from one of the Wiesmann videos, and this is the video it's from. All right, so this person's bending down, bending back up. But what we do to prepare our inputs, for use in Sparsey, is we edge filter. First, we probably cut out a little, box around here, region of interest, whatever, a box from the original video. We set the spatial resolution to, in this case, 42 by 60 pixels. We edge filter, then binarize, and then skeletonize each frame. So, and we do it each frame independently. So we're not using temporal information during the temporal context to assist in creation of these sequences. Anyway, so this is what's happening here, I think, is readily interpretable to a normal human being. They can just look at this and right away see, well, that looks like a person bending down, right? So there's enough information here for a human brain to understand what this is. So this is why was one reason I choose to use this type of preprocessing for Sparsey inputs. And there would be analogous preprocessing methods for auditory inputs as well. You could do that, or for somatosensory or olfactory or gustatory. Any sense modality could be processed in a way that is cognizable by a human. Anyway, so this is the sequence. That's the sequence we're going to present to this model. So let me now load this sequence. And I'll present the first frame. So present the first frame, this is what happens. The pixels corresponding to this frame are activated at level 1. They will send signals up through the projection of fibers, bottom up, feed forward fibers from this region of thalamus to this region of V1 cortex, to these macrocolumns. And a subset, macrocolumn is the more general term for the mesoscale circuit of cortex, and it's believed to be, I believe it to be, and I think a lot of people also do, not just in V1, but throughout sensory cortices and perhaps into prefrontal and inferotemporal and so forth. I see it as the fundamental mesoscale circuit everywhere. But here we're looking at, I guess you could think of it as just sensory cortices, visual sensory cortices. In any case, some subset of the coding fields that roughly overlie the regions where a contour exists in the input space become active, and they become active because they've met a criterion. So if I click on this rose, and these are the rose-colored macrocolumns. Again, you can't see the winner-take-all columns or the cells within those columns in this picture. What we see here, though, is an example of the wiring, and we see the receptive field. So let me switch to not use 3D for a second. So this is a plan view of the input level, 42 by 60 pixels. And what you're seeing here in cyan is the exact receptive field. This is the patch of LGN projection cells that project to the coding field, which I will call macrocolumns sometimes, or just max. even though, as I've already said, I'm really talking about the L23 portion of a macrocolumn. So if I say coding field or Mac, these are synonymous for the rest of this presentation. And there are 5 active pixels out of I think it's like 19 in this one. We'll get that information up later. And let me go back to 3D. So, one of the parameters of the model is the number of active pixels required in a coding field's receptive field in order for that coding field to turn on and activate a code in response. And if it's the first instance, to increase the weights from the active input units, in this case, individual pixels, to all the coding units, all the active coding units, or the active coding units in the coding field. So just one of the design criterion or design principles of this model is that the connection from a receptive field to a coding field is complete. It's a complete matrix. So all the pixels in that cyan patch connect. Each of them connects to all of the coding field units. So it's all to all, or a complete matrix, feed-forward matrix to the coding field. And that's true for every Mac at every level. So the magenta show top-down connections from overlying Macs in the next higher region cortex, in this case V2. And the green connections show horizontal or intrinsic connections from other Macs that are neighboring the Mac that I've selected here. So in this particular example, the specification of this network was such that all all the Macs that are immediate neighbors of a Mac have a complete projection to it. And the semantics of the horizontal connections are that they mediate signals from the prior time step. So basically, when we pick a code in a Mac at any level, but in this case, the one I'm moused over here, when you pick a code at time t, it's going to be a function of the computation computes a function of the inputs from the prior time step of the surrounding Macs, and also recurrently from the Mac itself, from whatever code was active in the Mac at t minus, in that Mac at t minus 1. So it computes a function of that, and also if there was an active codes in the level above, it would also multiply in those signals as well as what's coming up from the bottom. So it's a three-way combination of signals that determines what exact code, what set of Q units will become active in a Mac whenever the Mac meets its criterion for becoming active, which thus far is just a criterion on the number of features active in its bottom-up receptive field. We could do similar criteria for its horizontal receptive field and for its top-down, but that's not implemented or researched yet. In any case, it's this three-way combination of signals, and it's essentially analogous to a Bayesian network multiplying a likelihood times the current input to get a posterior distribution, except that unlike all of Bayesian network research, as far as I know, this model uses connections. It uses distributed codes for the variables present in the coding field, and distributed representations of the relationships between codes. So we'll go into that detail some other time. But anyway, so let's go to the next time step just to see kind of what's happening here. On the next frame, do one frame. So this is not much has changed. This person started, like we look at the first two frames here, right? Well, first frame, second frame, just the head starts to bend. So most of the edges stay pretty much where they were. On the second frame, this is the set of Macs that become active. So notice that, let's see, there are 100, this count here, active features, count 130. That means there's 130 pixels active in the input level on this second frame, or I suppose it's the third frame, right? Because, and there are, how many active macs? There are 70. So one thing to point out here is that a feature that's present in the receptor field of I'm going to get rid of these for a second, so it's a little easier to see. I'm getting rid of the horizontal connections. Not getting rid of them, I'm taking them out of view, obscuring them. When this, so this max receptor field has this particular feature, which we could, if we go to, would look like this. Doesn't matter if these are roughly convex, roughly circular, especially as you scale up. Receptor fields, doesn't matter that they're not exactly circular or anything like that. And there are 5 active pixels in it. So we go back to 3D now. What you notice is that one thing to notice rather, is that if I select a neighboring MAC that's also active, its receptor field is in general going to be overlapped. There's a lot of overlap of the receptor fields. And that means that 2 neighboring active MACs at V1 here, level 1, V1, are actually partially redundant. They're recoding some of the same information. If we go back and look at the plan view, you can see the overlap better. So this is the receptor field of one of them, and this is the receptor field. So in this case, it's actually exactly the same set of 5 pixels that are active in each of these 2 receptor fields. So it's completely redundant in coding at level 1 in these 2 coding fields of this particular feature at this particular frame of this particular sequence. That level of redundancy is fine. There's value to redundancy or to partial redundancy that I won't go into just yet. Okay, so one other thing to show is that as we move up the chain, you see that the receptor field, let me take away most of the blues, all the blues. The receptor field of this L2 or V2 MAC is actually a union, is a roughly circular patch of V1 MACs. So at this particular moment in time, these darker rows colored, maybe they're violet colored MACs at L1. Let's show this in plan view. This is level 2 now. So this is the receptor field of that level 2 MAC, the bottom up receptor field, right? The patch of L1 MACs that is the receptor field of the L2 MAC. And we see that 1, 2, 3, 4, 5 of those MACs are active right now. That means there's a code active. There are 5 of these codes active. And they have this rough topological relationship to each other. They fall along sort of a line coincident with one of the larger scale edges of this moving structure in the input in the world. The active L2 MAC, whose receptor field this is encoding a feature recursively through V1, that exists at the input level, but it's actually encoding it in terms of discrete codes of partial feature, of subsets of that overall feature. 5 of them, which might be overlapped. So let's go back to 3D. Let's see if I can show you that a little better. If I first of all, let's put this recursive on. Use recursive fields. Okay, so recursive fields means when I select this L2 MAC, you can see the L1 patch that is its receptor field at L1, and then you can see the ultimate input level receptor field that is the union of the pixels in the receptor fields of all of these L1 MACs. So you can see the recursive, the fan in, fan out, whatever, to show what areas of the input space reflect what areas in V1 or V2 or V4. If I select this guy, you can see that the region of the input space that ultimately influences the codes activated in and stored in an L3 MAC, let's say a V4 MAC, is that large portion of the input space. So now so that L3 MAC is actually active. Now let's select one of the L2 MACs that is causing that L3 MAC become active. And you can see its recursive via the recursive projection of its receptive field that it's actually this L2 MAC is actually coding this particular feature right now, this subset of pixels. If I simultaneously select this active L2 MAC, also part of this receptive field of this unit, you can see that it's picking up a little bit intersecting, but another portion of a larger vertical contour of this person who's bending down. So along their backside and back of their leg, and that's what the code active in this green outlined MAC at this time is represented. More precisely, though, it's not just representing this spatial feature present at this particular time. Is actually, as I said, the code will depend on inputs coming from the prior time step at any neighboring MAC, and from itself or any neighboring MACs that would have been active on the prior time step. In addition to this, the code persistence, the number of time steps that codes stay active, increases as we go up the hierarchy. So codes at V1 stay active for one time step. And this is by design. This is an a priori design element of the model. Excuse me. Codes at V2 stay active for two time steps, and codes active at V4 stay active for four time steps. The exact progression or schedule of increase is something that could be set, is a parameter of the model. But in general, and I call this persistence, codes persist for longer as we move up the hierarchy. So there's a lot of evidence for this there's a lot of evidence for this in cortex, that the codes stay on longer at higher levels. And that's another discussion. Anyway, let's look again at the plan view, so you can see the overlap of the two. Right, the overall cyan patches for the selected V4 MAC, and the two darker cyan patches are the receptive fields of two of the active V2 MACs that are causing that V4 MAC. So the V4 MAC is really, at this moment in time, is encoding this whole feature, all the black pixels. It may actually be encoding more because there's two more active V2 MACs in that V4 MAC receptive field that I haven't selected. I can go back and do that. But what you see here is that the V2 MAC, this one, is coding for this portion of this longer line, which in this case happens to be coincident with, and the other selected V2 MAC is coding for this portion, and they happen to be coincident in this case. The V4 MAC is therefore encoding a longer segment that is, represents a longer contour. It could have been that, and we'll see in other examples if I would go through it, that it could have been that on some particular frame, the set of pixels active in this MAC's receptive field, were at a right angle, and that therefore the V4 MAC would be encoding something like a corner at the scale of the V4 MAC, right? But in this case, it's a continued straight edge that is a combination of two aligned straight edges of smaller scales. So basically, the codes, as you move up the hierarchy, the codes code for progressively larger spatial scale features. And also, because of this graduated persistence property, they code for longer temporal. So it's basically, these codes are really for spatiotemporal features of progressively higher scales. There's just a lot that we could dive into about this, and a lot of analysis could be done, but this purpose of this talk is to just give an initial flavor of sort of the structure of Sparsey models and the degrees of freedom, or what can be represented and modeled. Let me go back to 3D for a moment. Right, I said I would do this. Let me just also simultaneously select the other two L2 MACs that are active in the receptive field of that active L4 MAC. If we go back down to level 1, we see now that actually almost all the pixels that are present, that are active in the receptor field of the L4 MAC, almost all of them, well, that's not true. All of them that fall along this line, except for these 4, are picked up by the union of the 4 codes for V2 MAC codes active. What's not, even though this portion of the image, active pixels, input pixels, it falls within the V4 MAX receptor field, they're actually not part of the feature being encoded here. Neither are these 4, but in particular, these 4 aren't. And that's because of the peculiarities of the wiring, the statistical idiosyncrasies of the wiring, which are done probabilistically, which preserve spatial locality and topography approximately as you move up the hierarchy, but in conjunction with the precise receptor fields of the V1 MAX and V2 MAX, and with the criterion number of active pixels for which they become active, the V1 MAX, or criterion number of V1 MAX, active V1 MAX, that a V2 MAC requires to become active. Because of the idiosyncrasies of those parameters, it just so happens that V2 MAX didn't become active whose receptor fields covered this portion of the image on this frame. Let's move to the next frame. Let's just see what happens on the next frame. We could do 1 frame. So on the next frame, MAX are active. We see that this feature's moved a little bit. I'm just trying to go further. You can see what's sort of happening on this frame. Only a small fraction of the pixels falling in this V4 MAC. I want to see if it's even active at this point, this V4 MAC. It is. It's still active. Oh, it's active because it stays on for 4 time steps. So when it becomes active, if it's inactive, it has to meet this bottom-up criterion of number of features in its receptor field to become active, right? But once it's active, it stays on for 4, even if the number of features, or in this case, number of active V2 MAX in its receptor field falls below. So this is a picture of what I've just been describing, that just shows, the 14 frames of the sequence and, the MACs that become active on each frame at L1 and L2, or at V1 and V2, not V4. This actual model only had 3 levels, but it's the same principles. And you can see the actual codes. Here you can see the details, the sparse distributed codes becoming active at each time step. If I scroll down here, this is a 3D vision, a 3D visualization of the same thing. We're seeing here a subset of the bottom-up weights, which are in blue, which are causing codes at V1 MAX and then V2 MAX to become active, over the course of this input. If you look here, this visualization video just shows, I guess, 1 MAC, some of the activity, the code's active and the signal's active, horizontal, bottom up, active at this MAC over the frames, and you can see the features in the L1. I'm sorry, this is a V1 MAC. You can see the features in its receptor field that are active on each of the frames. Notice that this receptor field here is much bigger than the one in the prior model. So this is another parameter to be explored in overall hierarchical models, is how big should the receptor fields be at each level to optimally encode, with natural input, natural data sets, natural visual data sets in this case. All right, let me stop there.